Hello, and thank you for joining me on this peaceful journey. Tonight, we will slowly drift into the long story of human flight, beginning with our earliest ancestors who stood beneath open skies and watched birds carve silent paths through the air. Imagine ancient grasslands at dusk, where migrating flocks moved in graceful formations overhead. And early humans wondered how wings could carry a body across such vast distances. Over centuries, that wondering gave rise to myths of sky gods and fragile attempts at gliding, to sketches drawn in the notebooks of inventors, to wooden frames stretched with fabric along windy shores. We will float through the rise of balloons warmed by fire, the focused experiments of two brothers on sandy dunes, the steady hum of propellers, the thunder of jet engines, and the towering ascent of rockets leaving Earth behind. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. Long before the hum of engines or the sweep of metal wings across the horizon, humanity's gaze turned upward. Beneath expansive skies, early humans watched birds tracing endless patterns across the air, their feathers glinting faintly in the sunlight, wings stretching, tilting and dipping with effortless grace. In these quiet moments of observation, questions stirred in the minds of those standing on plains, mountains, and river valleys alike. What would it be like to rise above the earth, to leave the soil and the known world behind, and touch the space where wind and sky entwine? The migration of birds became a silent classroom, teaching the principles of lift and balance long before the concepts had names, before the sciences of aerodynamics and physics were formalized. Stories and myths began to emerge as humanity sought to reconcile longing with caution. Tales like Icarus climbing toward the sun on waxen wings reflected both aspiration and the natural limits that must be understood before flight could ever be mastered. Across continents, early civilizations wove similar narratives, attributing winged powers to deities and spirits, capturing the tension between freedom and peril. Archaeologists today trace these inklings in cave paintings, in carvings of birds and flying creatures, in motifs of ascension that whisper of an ancient fascination with leaving the ground. These visual and oral traditions hint at the emotional scaffolding upon which future engineers and inventors would build. Even as the first humans experimented with rudimentary kites or swung from branches to emulate the flight of a hawk, imagination was as vital a force as observation. Wind currents, cloud movement, and thermals were studied instinctively, their subtle patterns observed for signs of opportunity or warning. Night skies offered their own lessons. The spread of stars and the shifting of moonlight revealed movement, rotation, and trajectory on a cosmic scale, offering perspectives that would one day influence navigation in the air and beyond. In this chapter, we drift through the collective dreams of our earliest ancestors, understanding that flight began not as a mechanical endeavor, but as a quiet, patient yearning. The human mind, captivated by the effortless motion of wings, laid the groundwork for centuries of curiosity, experimentation, and wonder. From the sway of birds in the sky to the first mythic flights of wax and feather, the story of aviation begins in the minds and imaginations of those who first dared to lift their eyes from the earth and dream. Beneath the vaulted ceilings of Renaissance workshops, ink met parchment in a delicate marriage of curiosity and invention. Leonardo da Vinci, the polymath whose mind spanned anatomy, mechanics, and art, sketched the earliest serious attempts to understand flight as a science. His notebooks reveal ornithopters with articulated wings, gliders with elongated frames, and rudimentary devices meant to mimic the flapping motion of birds. Each sketch captures subtle observations: the curvature of a wing to catch the wind, the angle of a lever to provide lift, the tension in a cord that might control movement. Though these machines never left the ground, the designs convey an astonishing comprehension of airflow and balance, a tactile intuition centuries ahead of its time. In exploring these creations, we see the intersection of artistic vision and empirical reasoning. Leonardo's drawings are filled with notations on friction, pressure, and the weight distribution required for human flight, demonstrating that careful observation of nature could inspire mechanical ingenuity. He studied birds in motion, their feathers, and the precise alignment of their wings in both gliding and flapping, attempting to translate those natural movements into achievable designs. Each page of his notebooks is a meditation on the invisible forces that govern lift and gravity, a bridge between wonder and structured experimentation. The Renaissance atmosphere itself encouraged a melding of imagination and calculation. Scholars, inventors, and artists were part of a larger community that valued observation and reflection. Leonardo's explorations were complemented by studies of air currents, wind tunnels of the mind, and sketches of rotating propellers, even though practical materials and engines for sustained flight would not yet exist. These studies laid conceptual groundwork for centuries of experimentation, proving that observation could be harnessed with precision to understand and replicate natural motion. While no human took to the air on Leonardo's contraptions, the philosophical and mechanical ideas embedded in his notebooks echoed across generations. Later, aviators and engineers would draw on the same principles of lift, wing shape, and stability he documented, refining and applying them in ways he could only imagine. His work illustrates a crucial turning point in the history of flight. Humanity had begun translating wonder into systematic inquiry, merging the beauty of visual imagination with the foundations of aerospace reasoning. Through this lens, Leonardo's sketches are not just drawings, but portals, inviting us to witness the evolution of human thought as it stretches toward the sky. Each line and annotation embodies both a yearning to rise and an enduring commitment to understanding the forces that make it possible, bridging centuries of aspiration with the scientific exploration that would one day allow humans to take flight. The 18th century opened a new chapter in human flight, not through wings or gliders, but by harnessing the buoyancy of heated air. In small towns and open fields of France, the Montgolfier brothers, Joseph Michel and Jacques Etienne, experimented with lightweight materials and simple principles of physics to lift objects above the ground. They observed that smoke from their hearths and rising plumes of hot air seemed to defy gravity, drifting upward with a soft, undulating motion. Inspired, they designed the first functional hot air balloons, constructing envelopes from silk and paper, carefully weighing every seam and considering how the rising heat would carry the craft skyward. On a crisp morning in 1783, the Montgolfier brothers launched their first manned ascent over the countryside, an event witnessed by crowds who gasped as the fragile sphere rose, billowing gently into the blue expanse above. The balloon's envelope swelled as warm air inside became less dense than the surrounding atmosphere, creating lift. This principle, deceptively simple, marked humanity's initial triumph over the firm grip of the Earth. Passengers inside, or in earlier experiments, animals such as sheep, ducks, and roosters, drifted effortlessly through the sky, propelled by forces invisible to the eye, yet precise in their effect. These first flights captured the public imagination, demonstrating that the realm of the air could be entered without wings, propellers, or engines. The science behind the Ascent is rooted in density and pressure. Heated air molecules move faster, spreading apart and reducing the overall density of the air inside the balloon compared to the cooler atmosphere surrounding it. The pressure differential allows the lighter envelope to rise. The Montgolfiers had observed this carefully, adjusting the size of the balloon and the intensity of the fire to achieve controlled lift, a delicate balance between heat, weight, and the surrounding wind currents. These experiments also revealed early lessons in stability. A balloon must remain symmetrically filled and tethered or vented to avoid tilting or spiraling uncontrollably. Crowds gathered in villages and city squares to witness these ascents, their awe mingled with skepticism and wonder. The sight of a vessel rising slowly above rooftops and trees became a symbol of possibility, a demonstration that human ingenuity could extend into realms previously reserved for birds and deities. Artists and engravers captured the moment in prints and sketches, portraying the colorful envelopes hovering above rivers and meadows, their shadows stretching across fields in long, soft arcs. These images contributed to a collective consciousness in which flight was no longer fantasy, but an observable, measurable reality. Following these initial flights, lighter-than aircraft evolved rapidly. Hydrogen airships and dirigibles incorporated principles learned from the Montgolfier's trials, combining buoyancy with rudimentary steering systems. Engineers began experimenting with elongated shapes to reduce drag, venting systems to control ascent and descent, and improved fabrics to resist tearing and heat exposure. Even as the age of rigid airships approached, the lessons of silk and fire, careful attention to lift, material integrity, and environmental interaction remained central to the understanding of flight. The Montgolfier brothers' achievement represents a critical pivot in aviation history. For the first time, humans truly left the ground in a controlled and observable manner, bridging the gap between observation and mechanical application. Their ascent carried not only passengers, but an idea that flight could be engineered, studied, and eventually perfected. The elegance of the balloon, rising silently with the sun casting long shadows over the countryside, reminds us that early aeronautical innovation relied not on engines, wings, or speed, but on patient observation, understanding natural forces, and trusting the delicate interaction between heat and air. Even centuries later, as powered flight dominates the skies, the memory of silk and fire lingers. Balloon festivals, colorful balloons drifting over valleys, echo the original experiments in their beauty and grace. The simplicity of hot air rising in a controlled envelope foreshadowed heavier-than aircraft, supersonic jets, and spacecraft that leave the atmosphere entirely. By lifting gently into the sky, the Montgolfiers transformed a philosophical dream into a tactile reality, proving that humans could ascend, measure, and explore, setting the stage for gliders, powered airplanes, and beyond. Long before engines hummed across open skies, human curiosity turned toward harnessing the invisible currents that flow above the Earth. In the 19th century, aviation pioneers such as Otto Lilienthal began translating observation into methodical experimentation, seeking to understand lift, drag, and stability through carefully designed gliders. Lilienthal, often called the Glider King, studied birds with meticulous attention, noting how they adjusted the curvature of their wings to control speed and direction. He then applied these insights to his own constructions, creating wooden frames covered with tightly stretched fabric that could bear the weight of a single human while tracing arcs through the air. Each flight was measured, each landing recorded, as he sought patterns in performance, documenting how changes in wing shape influenced the balance between lift and resistance. The principles of aerodynamics began to emerge not as abstract formulas, but as lived experience. Lilienthal's notebooks detail angles of attack, wing camber, and the distribution of weight along the fuselage. By launching from gentle slopes and gradually increasing height, he was able to test the effects of airflow over curved surfaces and the subtle interplay between gravity and lift. Every glide taught lessons about controlled surfaces. Small adjustments could determine whether the craft remained level, tilted, or spiraled. These discoveries laid the groundwork for heavier-than-air flight, demonstrating that propulsion alone could not guarantee stability. Understanding the forces acting on a winged body was equally essential. Across Europe and America, other innovators followed similar paths, building biplanes, monoplanes, and experimental gliders, each iteration refining the balance between structural strength and lightness. Materials were chosen for both resilience and minimal weight, reflecting an early understanding that aerodynamics depended not only on design, but on the interaction of air with every element of the craft. The curvature of wings, the placement of rudders, and even the angle of pilot positioning were all calculated to optimize lift while minimizing drag, creating a template for later powered flight. Wind tunnels and small-scale models, though primitive by modern standards, allowed systematic observation of airflow and stability, turning trial and error into a disciplined scientific exercise. Lilienthal and his contemporaries documented hundreds of flights, noting how air currents over ridges, thermals rising from sun-warmed ground, and gusts through valleys affected performance. These early aerodynamic studies bridged the poetic fascination with birds and the precise engineering that would guide the Wright brothers in their first sustained flights decades later. The gliders were silent teachers, demonstrating principles of air resistance, pressure gradients, and lift distribution that remain foundational to modern aviation. The risks were tangible and constant. Many pioneers faced crashes and injuries, learning firsthand how subtle miscalculations could lead to sudden drops or flips. These experiences informed refinements in wingspan, angle of attack, and pilot control, transforming raw experimentation into replicable science. Each controlled flight became a narrative of careful observation, measurement, and adjustment, emphasizing patience over spectacle. The lessons of gliding were as much about understanding human limits as mastering the air itself. Glider experiments reveal the inseparable relationship between natural forces and human ingenuity. By observing how wind shaped motion and how curvature created lift, inventors laid the foundation for powered aircraft that could navigate not just downward slopes, but open skies. The insights gained from the arcs of gliders descending hills and slopes influenced control surface design, rudder functionality, and the early mathematical modeling of aerodynamics. These flights taught that balance, precision, and responsiveness were essential to achieving sustained human flight. Through windswept fields and across rolling hills, the 19th century pioneers of gliding charted a new path for human aspiration. Their work bridges centuries of imagination, from mythic flights of wax and feathers to measured exploration of air currents, and demonstrates that mastery of lift, drag, and control is as much an art as a science. The gentle arcs of their craft, traced against clouds and sunlight, show how careful observation and patient refinement transform curiosity into knowledge, guiding the evolution of aviation toward engines, propellers, and, one day, the first powered flights that would defy gravity on a scale never before imagined. At the edge of the North Carolina coastline, where winds sweep across sandy dunes and the Atlantic hums in the distance, Orville and Wilbur Wright prepared to transform centuries of human aspiration into tangible achievement. The year was 1903, and after decades of observing birds, studying gliders, and meticulously recording aerodynamic principles, the brothers were ready to test their powered flyer. Unlike previous inventors, they approached flight as an engineering challenge, requiring careful measurement, rigorous experimentation, and innovative design. Every element of the flyer, the wing curvature, the control surfaces, the lightweight engine, was crafted with precision, reflecting lessons learned from gliders, wind observations, and years of trial and calculation. The flyer's structure was deceptively simple. A wooden frame supported fabric-covered wings, while a small hand-built gasoline engine provided thrust through a pair of counter-rotating propellers. The three-axis control system, which allowed pitch, roll, and yaw adjustments, was revolutionary, giving the pilot the ability to steer and stabilize the craft in a manner no other machine had achieved. The Wright brothers tested components repeatedly in their wind tunnel, refining designs based on data rather than intuition alone. These preparations were critical, ensuring that when the flyer left the ground, it would not merely lift, but remain controllable in the unpredictable environment of open air. On December 17, 1903, under overcast skies and gusting coastal winds, the flyer lifted off the sand for the first time. The initial flight lasted just 12 seconds, covering roughly 120 feet, but it marked the first sustained, powered, heavier-than-air flight in history. Each subsequent attempt that day built upon the last, with flights reaching longer distances and smoother control. Observers, including local witnesses, marveled at the strange bird-like craft gliding against the wind, a human creation temporarily defying gravity, translating decades of abstract theory into visible motion. The flyer's brief ascent symbolized a culmination of centuries of imagination, from mythic dreams to empirical investigation, and signaled a new era in aviation history. The significance of Kitty Hawk lies not only in the moment of lift, but in the systematic methods the Wright brothers employed. They meticulously recorded engine performance, wing loading, and the effects of wind and pilot adjustments. This attention to detail allowed their successes to be reproducible, laying the foundation for engineering standards in aviation. By documenting every measurement and iteration, they established flight as an applied science rather than an art of experimentation, creating principles that informed the design of aircraft for decades to come. The coastal environment played an essential role in their achievement. Steady, predictable winds allowed controlled takeoffs, while the soft sand of the dunes offered forgiving landings for a fragile machine. The brothers spent countless hours observing local wind patterns, the behavior of clouds, and the contours of the terrain to determine optimal flight conditions. This integration of environmental understanding with mechanical innovation illustrates a broader principle. Successful human flight relies as much on studying the atmosphere as on constructing engines and wings. Beyond the technical triumph, Kitty Hawk represents a turning point in human exploration. The flyer carried more than just a pilot. It carried the accumulated knowledge of centuries, from early myths of flight to the careful glider experiments of Lilienthal and others. Each rotation of its propellers converted principles of lift and propulsion into motion, creating a bridge from the imagination of ancient observers to the age of commercial and military aviation that would follow. The Wright brothers' achievement was a testament to careful observation, iterative design, and unyielding curiosity, proving that powered flight could exist within the bounds of scientific reasoning rather than hope or luck. As the flyer skimmed over sand and against wind, it left behind a legacy of inspiration and instruction. Subsequent generations of engineers, pilots, and dreamers drew upon these first controlled flights, improving engines, wings, and materials, and extending human reach beyond the dunes of Kitty Hawk. From that first lift to modern aircraft soaring across continents, the principles developed by the Wright brothers continue to govern how humans conquer the sky. Their work transformed a centuries-old desire into reality, offering a tangible demonstration that careful study, combined with ingenuity and daring, can translate dreams into sustained motion through the air. The outbreak of World War I in 1914 marked a dramatic turning point in the history of flight, as nations turned the fragile experiments of the previous decade into tools of reconnaissance, strategy, and combat. Aircraft, once considered novelty inventions, became essential instruments of military planning, carrying observers over enemy lines to survey fortifications, troop movements, and supply routes. The earliest reconnaissance planes were slow, open cockpit biplanes constructed of wood and canvas, vulnerable to both weather and enemy fire. Pilots endured chilling winds and the constant threat of structural failure, yet these missions demonstrated the strategic value of controlling the air, sparking an urgent drive to improve speed, durability, and maneuverability. As the conflict deepened, engineers responded with rapid innovation. The development of synchronized machine guns allowed pilots to fire through the propeller arc without destroying their own aircraft, transforming the airplane into an offensive weapon rather than a passive observer. Airframes were strengthened and metal fittings began replacing purely wooden structures, increasing resilience without excessive weight. Engine power increased steadily, with more efficient piston engines enabling higher altitudes and faster speeds. Aerodynamic refinements, such as tapered wings, streamlined fuselages, and improved propeller efficiency, emerged in response to the demands of aerial combat. Each technical advance was guided by a combination of battlefield necessity and iterative experimentation, producing aircraft that could endure the stresses of dogfights and long reconnaissance flights. Pilot training evolved alongside machinery. Early aviators often learned through direct exposure, gaining experience through trial flights and mentorship. But wartime exigencies accelerated structured instruction. Flight schools were established to teach navigation, formation, flying, and aerial tactics, emphasizing both skill and instinct. Navigation instruments, once minimal and rudimentary, advanced as well, incorporating compasses, altimeters, and rudimentary maps adapted for three-dimensional movement. These tools allowed pilots to operate beyond visual line of sight, expanding the operational range of aircraft and reinforcing the importance of integrated engineering and human performance. The demands of aerial warfare encouraged specialization. Fighters, bombers, and reconnaissance planes each evolved along distinct lines, optimizing design for speed, range, payload, or maneuverability. Observation aircraft needed stability and endurance. Fighters required agility and rapid response. Bombers demanded lifting capacity and structural reinforcement. Each category of aircraft reflected a careful balance between aerodynamic efficiency and functional necessity, producing innovations that would carry over into peacetime aviation. The rapid experimentation during this period, though driven by conflict, accelerated understanding of control surfaces, lift-to-drag ratios, and structural dynamics, creating a foundation for modern aircraft engineering. Even as these machines engaged in combat, the skies became laboratories for engineering insight. Pilots and mechanics observed the effects of high-speed turns, stress on spars and struts, and the impact of wind shear, recording data that informed subsequent designs. Every aerial engagement revealed weaknesses and possibilities, prompting incremental improvements to wing design, rudder function, and fuselage configuration. The challenges of integrating weaponry with flight performance spurred innovations in materials science, propeller aerodynamics, and engine cooling systems, demonstrating that the intersection of human skill and mechanical ingenuity could yield rapid advancements in aviation capability. World War I did more than redefine military tactics. It transformed the global perception of aircraft. Once whimsical or experimental, airplanes were now symbols of national power, technological sophistication, and strategic reach. Airfields, manufacturing facilities, and maintenance networks expanded, establishing infrastructure that would support commercial aviation in the following decades. The lessons learned in wind tunnels, testing fields, and combat zones informed designs that carried forward into the golden age of aviation, shaping expectations for speed, reliability, and operational range. By the end of the war, aircraft had evolved from fragile experimental gliders into sophisticated machines capable of sustained flight under challenging conditions. The period revealed the profound impact of aerodynamic refinement, materials engineering, and human adaptation on flight performance. It demonstrated that systematic experimentation under real-world conditions could accelerate innovation, transforming centuries of theory and curiosity into functional, reliable aircraft. These advancements set the stage for transatlantic flights, commercial airlines, and eventually the integration of jet propulsion, illustrating that even in times of conflict, the drive to understand and master the air propelled human ingenuity forward. The period following World War I brought a transformation in the way humanity perceived the sky. Aircraft, once instruments of reconnaissance and combat, began to capture the public imagination as vehicles of adventure, speed, and international connection. Pilots emerged as heroes, daring to push their machines across previously uncharted distances, testing endurance, reliability, and the limits of both technology and human resolve. The skies, once a realm of imagination and myth, became a theatre of possibility, with transoceanic and transcontinental journeys offering tangible proof that the world could be connected in hours rather than weeks. Charles Lindbergh's solo flight across the Atlantic in 1927 stands as an iconic moment of this era. In his single-engine Spirit of St. Louis, Lindbergh navigated through dense clouds, variable wind currents, and the vast, featureless expanse of ocean. His flight, spanning 3,600 miles from New York to Paris in 33.5 hours, demonstrated not only the endurance of pilot and machine, but also the growing sophistication of navigational techniques. Celestial navigation, dead reckoning, and an intimate understanding of weather patterns allowed aviators to traverse long distances with increasing confidence. Each journey illuminated the interplay between human skill, atmospheric science, and mechanical reliability, forging a new path for global aviation. Technological advances accelerated alongside these daring expeditions. Radial engines provided higher power-to-weight ratios and more consistent performance, while all-metal fuselages replaced fragile wooden frames, enhancing durability and resistance to turbulence. Airframe designs began to reflect aerodynamic efficiency, with tapered wings, smoother fuselage lines, and adjustable control surfaces contributing to stability and speed. Instrumentation also improved. Altimeters, airspeed indicators, and basic radio communication enhanced safety, allowing pilots to operate with greater awareness and control. The integration of these innovations marked a shift from experimental aviation to a field governed by engineering principles and repeatable outcomes. Passenger aviation emerged as a natural extension of these achievements. Early commercial airlines introduced small cabins and limited routes, offering travelers the novel experience of aerial mobility. Despite modest comfort and slow speeds compared to modern standards, these flights symbolized freedom and possibility. Passengers could traverse national borders in hours, a journey that previously required days by train or ship. Airports began to develop as hubs of activity, with refueling stations, maintenance facilities, and navigational aids forming the backbone of a burgeoning global network. The expansion of air routes fostered trade, cultural exchange, and international diplomacy, embedding aviation within the rhythms of daily life and global commerce. The Golden Age also fostered a culture of continuous experimentation. Pilots and engineers tested new configurations, from streamlined monoplane designs to retractable landing gear and enclosed cockpits, emphasizing safety, speed, and efficiency. Long-distance races, such as the Schneider Trophy competitions, encouraged the development of faster engines, lighter materials, and improved aerodynamics. Each record-breaking flight offered data that informed subsequent designs, creating a feedback loop where daring exploration advanced technical capability. The public followed these feats with rapt attention, and the era's iconic aviators became symbols of courage, ingenuity, and the promise of human achievement in the air. Visual storytelling of the period emphasizes sweeping coastal runways, sunlit fuselages glinting against the horizon, and aircraft climbing through clouds into the fading light. Interiors reveal pilots navigating with maps, instruments, and a keen awareness of weather, while passengers peer through small windows, witnessing the vastness of the sky. The juxtaposition of mechanical innovation with natural beauty underscores the allure of flight, reinforcing how aviation transformed both perception and reality. By the end of the 1930s, the foundations of modern air travel were firmly established. The integration of more reliable engines, all-metal construction, improved aerodynamics, and systematic navigation allowed commercial airlines to offer regular, predictable service. International air routes linked continents, connecting people, cultures, and economies in ways that were previously impossible. The daring feats of individual pilots, combined with meticulous engineering, had turned flight from spectacle into an enduring infrastructure, laying the groundwork for the jet age, supersonic transport, and the eventual exploration of space. The golden age of aviation, therefore, represents more than a series of record-breaking flights. It embodies a shift in humanity's relationship with the sky. No longer merely a space of imagination or military utility, the atmosphere became a bridge across oceans and continents, a conduit for human connection and technological evolution. Each long-distance journey carried lessons in navigation, material science, and aerodynamics, shaping expectations for safety, reliability, and endurance. In this era, flight became both a dream realized and a practical reality, linking distant lands and preparing the world for the transformative advancements of the mid-20th century. The mid-20th century opened a new chapter in aviation, as engineers and pilots turned from propeller-driven aircraft toward the possibilities of jet propulsion. The concept of using compressed air and fuel to generate high-speed exhaust thrust promised unprecedented speed and altitude, liberating flight from the mechanical limits of pistons and propellers. Jet engines, with their continuous combustion cycles, allowed airplanes to accelerate more rapidly and maintain higher cruise speeds, enabling longer ranges and heavier payloads without sacrificing efficiency. This technological shift redefined aerospace engineering and expanded the frontier of human flight. Experimental aircraft became laboratories in motion, testing the limits of materials, aerodynamics, and human endurance. Early jets faced critical challenges. High airspeed generated intense friction, heating fuselage surfaces and stressing metal alloys, while airflow instability caused buffeting and control difficulties. Engineers responded with swept wings to delay shockwave formation, reinforced airframes to resist thermal and mechanical stress, and new alloys capable of withstanding both pressure and heat. Each design was informed by precise observation, trial flights, and incremental refinement, creating a body of knowledge that formed the foundation for commercial and military jets alike. Breaking the sound barrier emerged as a symbolic and scientific milestone of the jet age. As aircraft approached Mach 1, air compression in front of the wings generated shockwaves that could destabilize planes and stress structures to the breaking point. Pilots needed meticulous attention to control inputs, understanding how supersonic airflow affected lift, drag, and stability. On October 14, 1947, Chuck Yeager piloted the Bell X-1 beyond this threshold, exceeding the speed of sound for the first time in level flight. The achievement demonstrated that careful engineering and precise piloting could overcome what had long been thought an insurmountable aerodynamic limit. The experience revealed how phenomena such as sonic booms, shock-induced separation, and compressibility effects influenced aircraft design, prompting a re-evaluation of materials, wing geometry, and control surface placement. The implications of jet propulsion extended far beyond supersonic milestones. Military applications demanded fast interceptors, strategic bombers, and high-altitude reconnaissance planes, all leveraging the power and efficiency of jet engines. Meanwhile, civilian aviation was transformed as jetliners replaced piston-driven aircraft on long routes, reducing travel times dramatically and opening new possibilities for international commerce and cultural exchange. The first commercial jets, such as the de Havilland Comet and Boeing 707, integrated aerodynamic refinements, pressurized cabins, and advanced avionics, demonstrating that the principles guiding experimental supersonic research could be applied to everyday air travel. The visual landscape of this era reflects both engineering triumph and natural beauty. Jets ascend against clouds of pearlescent vapor, trailing condensation, trails that trace their high-speed paths across the sky. Cockpits reveal pilots monitoring instruments that record airspeed, altitude, and engine performance in real time, adjusting inputs as aerodynamics shift with each maneuver. On the ground, technicians calibrate turbines, examine stress points, and refine jet intake designs, contributing to an ongoing cycle of optimization. The human, mechanical, and environmental elements coexist in a dynamic interplay, demonstrating that advanced flight is as much about observation and adaptation as raw power. Aerodynamic theory advanced alongside jet technology. Understanding shockwave formation, supersonic flow, and high-speed stability guided wing design, fuselage shaping, and engine placement. Engineers incorporated delta wings, variable geometry controls, and swept tail configurations to manage compressibility and minimize drag. Fuel efficiency, thrust-to-weight ratios, and structural resilience became central considerations, balancing speed with safety and endurance. Each incremental advance informed the next, creating a continuum from early propeller-driven machines to sophisticated supersonic and eventually hypersonic aircraft. By the end of the 1950s, jet propulsion had redefined expectations of flight. Distances once measured in days were traversed in hours. Altitude ceilings expanded into the stratosphere, and the human experience of speed and scale shifted dramatically. Supersonic achievement proved that the boundaries of physics could be negotiated through innovation and precise control. Aerodynamic knowledge, materials science, and human expertise combined to create a new era where the air itself became a medium of unprecedented possibility, preparing the way for supersonic passenger travel, orbital vehicles, and exploration beyond Earth's atmosphere. By the 1960s, the vision of supersonic passenger travel had shifted from experimental ambition to tangible reality. Aircraft designers sought to combine speed, safety, and comfort in ways that had never been attempted before, aiming to carry civilians across oceans in hours, rather than the conventional transatlantic schedule of jets powered by propellers or early turbines. The Concorde, a product of Anglo-French collaboration, embodied this vision with a slender fuselage, delta-shaped wings, and afterburning turbojet engines capable of sustaining cruising speeds exceeding Mach 2. Its design required meticulous attention to aerodynamics, materials science, and thermal management, as the friction generated at supersonic velocities heated the fuselage to temperatures that challenged conventional alloys. The delta wing, a hallmark of Concorde's aerodynamic sophistication, allowed for stability at both high and low speeds. Its swept, triangular configuration reduced drag while providing lift, enabling the aircraft to ascend efficiently and cruise at altitudes above 50,000 feet. Engineers also incorporated adjustable nose cones that could droop during takeoff and landing, improving pilot visibility without compromising supersonic performance. Every component reflected a balance between cutting-edge technology and practical functionality, revealing the layers of scientific knowledge applied to civilian supersonic flight. Concorde's engines, Rolls-Royce/Snecma, Olympus 593 turbojets, demonstrated remarkable thrust and efficiency for their era. Afterburners provided bursts of additional power for takeoff and acceleration, while the aircraft's air intakes and nozzle designs optimized airflow across a broad speed range. Engineers contended with the intense heat generated by air friction at Mach 2, developing specialized materials and cooling strategies to maintain structural integrity. At cruising altitude, Concorde glided above a thinner atmosphere, where air resistance was lower, but temperatures on leading edges and fuselage panels reached levels that required constant monitoring. The aircraft's operation extended beyond technology into infrastructure and international regulation. Airports adapted to supersonic travel with longer runways and reinforced taxiways to accommodate higher speeds and greater weights. Noise considerations became critical as the sonic boom created by breaking the sound barrier restricted overland supersonic flight, guiding route planning over oceans and sparsely populated areas. Regulatory bodies, including civil aviation authorities, established protocols for airworthiness, flight corridors, and passenger safety, integrating Concorde into the broader commercial aviation system without compromising the rigor demanded by high-speed flight. Passengers experienced supersonic travel as both spectacle and convenience. Interiors were compact yet elegant, with pressurized cabins maintaining a comfortable environment at altitudes where the external air was nearly a tenth of sea level density. Windows offered glimpses of the curvature of Earth and the ethereal light above. Clouds, while the cabin vibration and hum reflected the power contained within the engines. Flights across the Atlantic could be completed in under 4 hours, connecting New York and London or Paris at unprecedented speed, compressing distances and redefining international travel. Despite its achievements, Concorde's era was limited by economics and environmental concerns. Operating costs were high, fuel consumption considerable, and noise regulations constrained potential routes. Nevertheless, the aircraft's legacy endures as a symbol of technological ambition and aerodynamic elegance. Its influence is evident in ongoing research into sustainable supersonic travel, advanced materials, and high-efficiency propulsion systems, which seek to reconcile speed with energy efficiency and environmental stewardship. Concorde demonstrated that human ingenuity could transform daring concepts into operational reality, inspiring subsequent generations of aerospace engineers and pilots to explore the boundaries of flight. The Concorde period represents a convergence of engineering mastery, regulatory coordination, and human aspiration. Its story highlights the intersection of physics, materials science, and practical aviation, emphasizing how innovation and meticulous design can create a machine capable of extraordinary performance. Supersonic passenger travel, showed that speed need not compromise safety or reliability, and that the dream of transcending conventional time barriers in flight could be realized, leaving a blueprint for future high-speed aircraft and a reminder of humanity's enduring fascination with the sky. As the 20th century progressed, human ambition turned skyward, pushing the limits of flight from the stratosphere into the vacuum of space. Rockets, powered by chemical propulsion, became the instruments of this next frontier, carrying satellites, probes, and eventually humans beyond Earth's atmosphere. Unlike aircraft operating within air, spacecraft rely on orbital mechanics, inertia, and precise trajectories to navigate the void. Launch sequences demand careful timing and coordination, as engines must generate sufficient thrust to overcome gravity and reach escape velocity, while guidance systems control pitch, yaw, and roll during ascent and orbital insertion. The space race accelerated technological innovation, beginning with the launch of Sputnik, won by the Soviet Union in 1957, followed closely by early American satellites. These milestones demonstrated the feasibility of sustained orbital flight and the importance of telemetry, control systems, and heat shielding. Human spaceflight soon followed, with Yuri Gagarin completing the first orbital circuit of Earth in 1961, offering a new perspective on our planet as a fragile sphere suspended in darkness. Each mission required life support systems to regulate oxygen, pressure, and temperature, illustrating the complexity of sustaining human activity beyond the atmosphere. The moon landing in 1969 marked the pinnacle of early exploration, combining multi-stage rockets, lunar modules, and precise navigation to allow astronauts to descend, explore, and return safely. This achievement relied on decades of cumulative aerospace knowledge, integrating lessons from supersonic flight, structural engineering, and propulsion research. Spacecraft had to contend with vacuum, microgravity, and radiation, requiring innovative materials and shielding techniques. Engineers also developed reusable components and modular designs, laying the groundwork for future spacecraft capable of multiple missions and extended orbital operations. Modern advances in space travel emphasize efficiency, sustainability, and versatility. Reusable launch systems, such as those pioneered by private aerospace companies, reduce costs and increase mission frequency. Electric propulsion technologies, including ion drives, enable long-duration deep space exploration with minimal fuel consumption, expanding the reach of robotic missions to asteroids, Mars, and beyond. Satellite constellations provide global communication, weather monitoring, and Earth observation, demonstrating that spaceflight is not only an avenue for exploration, but also a practical extension of human civilization. The visual and physical experience of spaceflight is unparalleled. Astronauts observe the curvature of Earth against the black void, witness auroras and meteor showers from orbit, and experience microgravity that allows effortless movement through spacecraft interiors. External cameras capture multi-stage rockets ascending against clouds of exhaust and flame, gradually shrinking into the blue atmosphere before vanishing into the infinite expanse. Each mission underscores the interplay of human ingenuity, engineering precision, and cosmic perspective, showing how centuries of flight experimentation converge in the ultimate frontier. Looking forward, the future of flight extends to interplanetary travel and colonization. Concepts for crewed Mars missions involve advanced propulsion, closed-loop life support, and radiation shielding to sustain humans for months in transit. Research into fusion engines, solar sails, and hybrid propulsion systems could reduce travel times to other planets, opening the possibility of exploring moons, asteroids, and exoplanets. Robotic precursors and orbital habitats are preparing the groundwork for this next stage, extending the principles of lift, control, and navigation learned from millennia of flight into a realm where air gives way to vacuum and gravity is no longer a constant companion. From early gliders to supersonic jets, and now to orbiting spacecraft, human flight has evolved as a continuous thread of curiosity, experimentation, and innovation. Each stage built on lessons from previous generations, culminating in the possibility of traveling to other worlds. The future promises not only the expansion of knowledge and exploration, but also new perspectives on Earth and our place in the cosmos, as humanity ventures further beyond its terrestrial origins, propelled by the same wonder that inspired the first glances skyward. As our journey through the story of human flight comes to a close, allow yourself to sink even deeper into relaxation. Picture once more the wide sky stretching endlessly above you, filled with the memory of canvas wings, silver airliners crossing continents, and spacecraft gliding into the dark beyond our atmosphere. Feel the steady rhythm of lift and gravity balancing in harmony. The same invisible forces that carried gliders over coastal winds and guided rockets toward distant orbits. Let the vastness of air and space feel expansive and reassuring, a reminder of how curiosity can lift humanity beyond the horizon. Feel your thoughts softly fading, your muscles loosening, and your breath flowing naturally and effortlessly. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.